By the end of this video, you should be able to go through that problem that was presented last week and look at the transient analysis and make some sense of the results. Now, the first thing we're going to do is basically recreate the geometry. Here I am in ANSYS, and I've created the geometry in SolidWorks, and now I'm going to construct an analysis. Now I've already dragged up a transient thermal here, and I've changed the engineering data to be aluminum, as you know. I've imported the geometry from a step file from SolidWorks. I called it Gremlin Disk. And I've opened up the model in Mechanical Modeler. So here we are in the Mechanical Modeler. All of these steps you're familiar with now. I imported the geometry, and the geometry has been updated. And it's just a round disc, 1 meter in diameter, 1 centimeter thick, with a 10 centimeter hole in the middle. Now I imported a few different materials, and I've got it set up at the moment as magnesium alloy. I could change that, change the material type. Instead of magnesium, I could make it aluminum. And since that's what I asked you to do in the problem, then that would be appropriate. And looking at the mesh, I've just created a fairly coarse mesh where I used an automatic method for choosing the geometry, and I selected the body, so I didn't make any faces unique. And I picked a sizing of an element size of 0.1 meters, so 10 centimeters, fairly large grid size, but because we're going to do a transient analysis, we need to make it rough because otherwise it'll take too long. Now, the problem that I'd given you was fairly poorly defined because I told you it was going to be a 1 meter diameter disc, so I've created that. I told you it would be 1 centimeter thick, so I've done that, and it had a 10 centimeter hole in the middle. Okay, and then it would be a transient analysis with heat generation. Well, the first thing was to set the initial temperature, and in my case, I set it at 0. The analysis settings, I don't know how long the analysis is going to run for, so I chose 300 steps. That's quite a long number of steps, and it will take a long time to compile. The other thing that I'd asked was for internal heat generation. And for that, I go up here to the boundary conditions, and you'll see that there's an internal heat generation parameter there. Now, that gets applied to the body, as you can see here, because it's a parameter that represents generation of heat from within the mass. You could think of this as if you have an electrical resistor, current is flowing through, and as the current goes through the material, it's heating up the material. In terms of a heat analysis, it's a bit of a weird concept. When you go back and do your mechanical analysis for structures, then this term actually behaves like gravity. So I've set that internal heat generation to 100 watts per meter cubed. And because I didn't define what the boundary was like, I've actually just set all of the boundary conditions up for all of the surfaces as being convection boundaries. And I specified a film coefficient of 10 watts per meter squared per degree C. That's a reasonable environmental boundary condition in air. And I set the ambient temperature up to be 0. So here we have a plate that starts off with its conditions. Everything is at 0 degrees C. And then we turn on some internal heat generation. You can think of it as if we have a resistor, starts off cold, and then we start driving current through it. and the current is evenly distributed, so the metal starts to heat up. And the solution, which I've already gone through, shows the transient temperatures at times. This makes an interesting looking plot. Now, if I go through the animation for this temperature, what you see is rather surprising. If I just look at a particular time, maybe you just did it wrong. So if we look at any particular time, the results look rather surprising because at each time step, the temperature is effectively constant in this aluminum plate. And the hottest temperature is at the end of the 300 seconds, but it just keeps getting hotter. The other thing that's a bit surprising is that it's only 0.01 degrees C change in temperature. As if. So what happened? Did we do something wrong? I think we followed the instructions. Well, maybe we should look again. Maybe the problem wasn't posed very well by the person who asked the question. I wonder if maybe we should rethink this and try to change the conditions. Guys, just settle down, okay? Come on. So we need to rethink this, and in the next video, let's look at it a different way. I got a problem for you. Ha!